Right, so the next topic are these Lobio number solutions to unsteady state heat transfer problems. And this has got its own special name, and it's a quick topic. It's called lumped parameter analysis. And we're doing the easy one first. So we just did the dimensional analysis of unsteady state heat transfer, and out popped the Biot number. So the Biot number is the number that helps us determine the ratio of the resistances, internal and external, in a problem. So the Biot number is the heat transfer coefficient times the characteristic length scale D, and we're going to find out what that is in the case of a low Biot number, what that turns out to be useful to choose, divided by the thermal conductivity. Then the time variable for the unsteady state solution is going to be expressed as a Fourier number. So that's alpha T over the square of the D. So during that conversation we just had, we said that the Biot number, because it's doing this balancing out of when these different resistances are high or low, there'll be three sort of, not surprised that there'll be three cases. The case where the resistance to internal heat transfer is high, the resistance to when the resistance to external is high and dominant, and the case where you can't say that either one dominates. So we're going to talk about the case where we have a low Biot number, which is the case where there's very little resistance inside the object. So this is the case that we kind of talked about before. We did an example when we studied the macroscopic unsteady state heat transfer. And in that case, we were talking about an object in a manufacturing site that was hot, and it got pushed out into an airstream that was cooling it. And we didn't worry about the temperature distribution inside the part. That is this low Biot number case. So if as soon as the part is exposed to air of a certain temperature, whatever the surface temperature turns out to be, wham, it propagates entirely throughout the entire object. So that's a nice case because we don't have to worry about the temperature distribution so much. We just say T, the object is at temperature T. So if you'll remember, when we talked about that kind of a problem, we said we would use the macroscopic unsteady state balance when we had an unusually shaped material as one of the reasons, or when we didn't care about the temperature inside the object. And so it becomes very sensible to choose this length scale as a ratio of volume to area, so that we have surface area A divided into the volume of the surface. And now we can talk about spheres, we can talk about cylinders, we can talk about hunks of coal, we can talk about a part that's been carefully machined into a very extreme shape, a new carburetor or something. So that's going to be the length scale that we're going to pick. And this, I'm going to say this a bunch of times because people get confused. This length scale is only used for this low Biot number case. It's only used in lumped parameter analysis. So use it in the lumped parameter analysis, but don't use it otherwise. It also turns out, and we'll talk about this when we get back to the third case, but we can figure out what's the maximum Biot number for it to work, to have a reasonable assumption that the temperature is constant inside the part, and the answer is 0.1. So when this Biot number, the one that's based on the volume divided by the surface area, is less than 0.1, that's the boundary. So write that one down. That one's the keeper. All right. So let's do a quick calculation to show how this lumped parameter analysis can work. And this is going to be another time where we're going to use this unsteady state macroscopic energy balance. So here's the problem. If we have a piece of steel that's dropped into a large well-stirred reservoir at a bulk fluid temperature, T infinity, what's the temperature of the steel as a function of time? Okay, so if, again, we're always asking ourselves, what if what if we were coming at this cold and we weren't positive that this was a lumped parameter analysis type of a problem? Which one would we use? This is a case of a part that has an unknown shape, and that's going to lead us to the unsteady state balance. And we're not being asked about the temperature profile or the distribution of temperature in the part. And so this is classic problem that uses the macroscopic balance. So that's going to be the one that we use. So here's the macroscopic balance, right? So I'm going to encourage some participation here so that we can try to practice simplifying the macroscopic balance and getting to the equation that we need to solve. So for this problem, right, how do you suggest we simplify the balance? We're going to pick a macroscopic control volume. It's basically going to enclose the part. Can you give me some things to slash away?
We can slash kinetic energy and potential energy.
Because?
They're it's insignificant.
Yeah, these are usually small for this type of problem. So neglect. Expect it to be small. Okay. How much enthalpy flows in and out?
We can also get rid of work shaft.
Yeah, what's the reason?
Because there's no like electricity or chemical reactions or anything.
Well, it's not so much the electricity. It's that there's no shaft. No shaft work. It's
okay.
So there's no pump, there's no turbine, there's no mixing bar. Okay.
Can you get rid of your delta H, delta EK, and delta EP because there's no flow?
Yeah. So the control volume is, the part's not emitting mass, so there's no mass flow rate, and so they go out. Does the internal energy change? So it was just recently, so you haven't studied it, haven't thought about it too much, but we talked about the things that cause internal energy to change are temperature, chemical reaction, and phase change. So is any of that changing in the part? Temperature, chemical reaction, phase change. It starts out hot and you throw it into a bucket.
Yes, temperature is changing.
So the temperature is changing. Is heat crossing the boundary? Yes. If it were adiabatic, you wouldn't expect this part to come out, go into a bucket and stay the same temperature. So there has to be some Q. And so we have to sort out these two terms. I'm making us move along a little bit here. This was from the other lecture where I summarized typical modeling assumptions for macroscopic unsteady. So this one is a keeper. It has the things we remembered, that the kinetic and the potential are often negligible, and that you have to flow, no flow, no shafts, no shaft work. And then here was a little piece that maybe we would have scratched our heads a little bit about, but we can write the mass of the system times its heat capacity times its temperature change, and that's going to go into our expression. So that's that. And then the Q, going back to the lecture notes, I gave you a summary sheet of the various Qs, and we just have to go down the list and ask, is there something in thermal contact with the part? And by the way, the question about this is not about air or water or liquid, because the air and water and liquid are in the heat transfer coefficient. So this is just asking, is this a problem where, let's say, metal meets metal? Yeah, it's basically asking, is this a problem where metal meets metal and energy gets conducted? So no. Is this a problem where metal meets liquid and there's a heat transfer coefficient? And that's what it is. Is this a problem where there are very, very high temperatures that would then make the radiation part be important? And you might be tempted to use this one, and then it would be the same problem we did in class last time. But the presence of a liquid, it makes the temperature of the part go down so fast and we did actually see in our last lecture that the radiation was small even when we had it in contact with a gas. So the radiation is also not important. There's no electrical potential. Okay, so it's not like there's a battery or something going across the part that's drawing current through it, and there's no chemical reaction going on. So there's really only one Q. So that makes it all just that much easier. So let's pull that together. So I'm going to pull this one. What do we have here? We have the mass of the system times its heat capacity, CV, CP, whatever we can find. dt equals HA delta T. So is the bulk, so the temperature is going down, and we have to match, so if we have to match the sign here, and it's going to be the bulk temperature minus the temperature of the part. So the bulk temperature is cold, the part is hot, and the temperature is decreasing as a function of time. So those signs all match. So remember, we're trying to do this Lobio number problem, and you see we have a single temperature for the part, and that's the Lobio number case where there's no internal resistance to heat transfer. We did the macroscopic steady state balance and considered all the ways that energy might cross the macroscopic boundaries, and we end up with this expression. And this is a differential equation we can solve. All right, so let's move all the constants to the right, HA over MCP. And there they are. And then we have T infinity minus T. And we're going to move that over to the left, move all the temperatures to the left and all the times to the right. So we get dt over T infinity minus T equals, let's call this B. That's my modus operandi, B dt. This is just the integral of du over u is equal to the natural log of u, as long as it's the integral of du over u. And so if u is T infinity minus T, then du is equal to minus dt. So du dt equals minus 1, except I needed the other t, the capital T. Okay, du is equal to minus dt. So I put a minus sign there and a minus sign out here. And now this is u over u, du over u. So when I integrate minus the integral of minus dt over T infinity minus T equals B times the integral of dt. So I get natural log of u. The minus is on the outside, B times T plus a constant. Always add our constant of integration. So now we need some initial conditions. T equals 0, the part is T naught. So that means we can calculate C1. So I can plug this in, calculate C1, put it back, and we have our final answer. Oh, I bet you that didn't work like that. Trying to be a little bit too clever. So because I see that I'm getting towards the end here, I'm speeding up a little bit. So here are the slides. There's the macroscopic energy balance. And then we tried it. And we made those assumptions that we talked about. And we looked at the list of the possible Qs. And we identified which ones are important. There's the list. We pulled together the ones that are not 0 to get a solution. So I wrote this down and put this on the right-hand side, and away we went. We've been solving it. And then once I put that initial condition in and finish the algebra, I'll get the final answer, which is this exponential relationship. So the lumped parameter method allowed us to get all the way to the end, because it only had the heat transfer coefficient. When we had the example we did previously that had radiation in it, we had to do the integration numerically, but also doable in Excel. Right? So this, we can write this expression in dimensionless form, and it turns out to be a simple relationship with the Biot number. A very, very simple result. Y equals e to the minus Biot number, Fourier number for the lump parameter analysis. So when the Biot number is small, and by small, we check the lumped parameter Biot number being less than 0.1, it's a very simple solution, okay? As I've said before, we only use that lump parameter characteristic length scale for lump parameter. So we have two more regimes to talk about, which will take up the remaining lectures of this this module 2, which is high Biot number and moderate Biot number, and those will be the next 2 things that we talk about. Right. So thanks for your patience. I did go 2 minutes over here.